let's review this problem, and I'll just take 10 minutes to discuss the non-recursive solution to this problem. So this is a graph traversal problem called course schedule. It's a very famous graph traversal problem. What it talks about is trying to order your nodes in a linear fashion. We've talked a lot about directed acyclic graphs, or DAGs, and there's actually an algorithm called the topological sort that allows you to order each of those nodes in a linear fashion. So our task now is to implement it for this problem in order to solve what we're trying to look for. So this problem is very real world. It asks, given these two inputs, num courses is integer and prerequisites it's a list. And what we have to do is we have to compare whether our prerequisites of our classes are actually legal and whether we are able to fulfill our course schedule given these prerequisites. So what it looks like is that given a list of prerequisites, so for example, course 1, in order to take course 0, we have to take course 1 here. So it's a little bit counterintuitive in terms of how it's ordered, but essentially we're given a list of lists. The first element, the one at index 0, is the class that we're interested in, and then the element in the first index, or the second element, is the prerequisite for the class in index 0. So we're given a list of these lists, and you can see here is one of our test cases. Is we have course 1, and 0 is a prerequisite for course 1. So we have to take course 0 first. And we're also given the number of courses 2. And what we expect for this test case is the output to be true, because there are a total of 2 courses we take. In order to take course 1, we have to have finished course 0. And this is a legal input. However, if we added 0, 1 in our prerequisites input, this would actually be false, because what we're saying is that there's 2 courses, a total of 2 courses we can take. In order to take course 1, we have to have finished course 0, but then we have another pair in which, in order to take course 0, we have to have a prerequisite course 1, which of course is not valid. So we expect the output to be false in these circumstances. So let's implement and solve this question. So given the number of courses and given the prerequisites and pairs of these courses, can we find a way to return true for valid prerequisites, and can we return false for invalid prerequisites? So I've already hinted at the beginning that this is a graph problem. So what we need to do is whenever you see a graph problem, you really want to first construct the graph out of these prerequisites, which are just edges. So one node is linked to another node, or one class is linked to another class. And in order to, after we construct a graph, we always want to keep a vision of how do we traverse the graph. So there's 2 famous ways of doing it: it's breadth first search and depth first search. And we'll do the non-recursive breadth first search for this problem, because in terms of implementing topological ordering or topological sort, a breadth first search is very intuitive. So in order to construct a graph, what we need to do is let's just make a graph variable, and let's just make a list of lists. And we're going to loop through every single course in num courses. So given 2 courses, we're going to create 2 lists inside this outer list. And then what we really need to consider when it comes to a topological sort is we need to track the in degree, or the number of edges that are coming into a node. In which case, the best way to think about this in this example is the number of prerequisites that come to a course. We have to keep track of how many prerequisites a course has. And in graph terminology, this would be called an in degree, or the number of edges that are coming into a node. And we want to create a list of the number of, we want to keep track and bookkeep the in degree for each of these nodes in this graph. So let's say that each node has no prerequisites, just as a priori assumption that keeps it clean. So, and of course, we multiply it by the actual number of courses. So, and we also need to have a range here. All right, so now that we've initialized our graph and we have our entry, let's get cracking. So let's loop through the edges that were given in the prerequisites, and let's populate our graph and our in-degree bookkeeping list. So let's say we're given, I tend to like, even though we're not dealing with trees, I really like the concept of parent and child being applied to graphs as well. Because this is a directed acyclic graph, so it's nice to kind of keep track of which node is leading into the other node. So even, and a tree is just a special type of graph, and it may be a little bit confusing to some, but I like calling these parents and child because I think that prerequisites of relationship is very well preserved by this terminology. And when we have a parent and a child, well, remember, it's very counterintuitive. So for when we have course 0, comma 1, it really means that the course 0 has prerequisite course 1. So in fact, it should actually be for child, comma parent. So this is just something when it comes up in interviews or comes up in real life, you have to really keep track of what the problem is. So now we populate our graph with our parent. And let's append the child. So what is this saying is that this is just saying that the parent node is directed into that child node, or essentially this parent class is the prerequisite for this child class. And let's also populate our in-degree with, of course, we know that the child has one edge going into it, and that is the parent node. So we have to increase the in-degree index position of this child to be equal to increment that by 1. So hopefully that makes sense, and let me know if there's any questions for now. But now that we've finished populating our graph and our list of the in-degree numbers for each of our nodes, let's start traversing. So as you may, if you're familiar with breadth first search, you know we always have to create a queue. And now when it comes to populating our initial queue, because we can't loop through anything unless we initialize some nodes for our queue first. So even without regards to the problem, we just think back to what we know before about breadth first search and queues, that we really do need some initial kind of nodes for our queue. And in this problem, in this circumstance, what we want to do is we want to loop through each of the courses that are provided to us in num courses. And if the degree of each of those classes is equal to 0, that's going to be our initial queue. So when it comes to topological sort, and when we want to start with initializing our DAG, we always have to start somewhere, and it makes very intuitive sense that we started with nodes that don't have any edges, that don't have any relationships, that are essentially standalone. And eventually we will find a node that does have an edge, but we always want to make sure we start with nodes that don't have anything. So that makes a lot of intuitive sense in my mind. So let's initialize them. So we're going to start with each course in our loop in course and num courses, and if the in degree of the course is equal to 0, and now we have a queue going, and of course now we want to traverse through our queue. So now, so let's actually make a for loop for this queue. So for each node in our queue, or shall we say, yep. So for now that we're looping through each node in our queue, we're also going to find the neighbors for each of the nodes for the current node that in the queue that we're on. So we're going to call this neighbor, and for neighbor, and then we're going to we're going to index the graph that we created earlier with that node. So we're able to find all the, because remember the graph is just a list of lists. So the one at index position of that node would actually be a list of that node's children. or that node's neighbors would probably be a better word than children. So now what we need to do is every time we traverse through the graph in a breadth first search manner, every time we hit upon a node, we want to decrement the integree of the neighbor by 1. So essentially, what this means is that we're removing an edge. We're trying to remove edges as we're traversing along the entire the neighbors of the queue of the current node that's currently in the queue. And the real reason why we want to remove an edge and decrement the integree by 1 is because when we're trying to do a topological sort, every time we hit upon a node, what we want to do is we want to say that this node has one fewer relationship. So we're able to essentially put nodes that don't have any relationships back onto the queue. And by doing so, what we're able to do is we're able to track and see if we can actually traverse through this entire queue, and if we're actually able to organize and create a directed acyclic graph out of the inputs that we're given. So if the integree of such a node in a neighbor is actually 0, we append the queue with the neighbor. So we keep going on indefinitely until we decrement enough of the integrees of each of these nodes so that the queue would have things left over, and the things and the nodes that or classes that are left over in the queue would essentially be the number of classes that we have, because these are classes that that would pass the prerequisite test and would actually allow us to finish all the courses. So we are essentially keeping a track of the queue is doubling not only as something that we're traversing over, but it's also counting as like an accounting bookkeeping mechanism that it's a running count of all the classes that we're actually able to finish. So what we have is if the length of queue is equal to num courses, we're going to return true if that is indeed the case, and for illegal cases, in which case it was false, we're actually going to return false. So let's run this code and let's test it. Can't multiply it by non-type of, oh yeah, so we don't need range here, but we definitely need range above. All right, so let's try running this code again. Int object is not iterable. So let's try to debug this. So, oh yeah, we need a range here. So always mine your range. So that's true. And let's see if this passes. So yep, so we're faster than 90% of Python solutions. And it seems that everything is in order here. So I would say that in terms of the problem, I think the trickiest part of this problem is essentially recognizing that we are doing a topological sort using breadth first search here. And we are essentially overloading the queue because the queue is not only something that we're traversing over, but it's also keeping a running count of the number of classes that we've actually finished at the very end. So the more nodes that we have append to the queue, that essentially has that terminate in that queue would actually be classes that we finished. And that would essentially track the number of courses that we've had. We could also have made it much more explicit by making a visited or a count set here and then try appending to that set as we traverse through the node. But I think this is a lot cleaner solution to recognize that our queue is also something at the very end. It represents all the number of classes that we have taken past, of course, because we've taken all the prerequisites into account as well. So yeah, that's it for me for today. Any questions?
Very cool.
Anything else? I think I'll pass it on to you, Matt.